All right, so let's move on to some new stuff that we haven't covered yet before. I want to try and spend maybe 10 more minutes on projectile motion because I think we'd like to see it one more time. It's not new stuff. It's just a little bit of muscle memory on this stuff. Do an example, and then we're going to move on to chapter 4. Okay. So let's consider a kangaroo rat. Kangaroo rat can jump a horizontal distance, a range, of up to 1.8 meters, which when you consider this cute little guy is pretty incredible. That's 15 times their body length, right? They've got big, gigantic legs for their body. So assuming that they launch themselves at 45 degrees, right, what's their launch velocity? So last time we got as far as deriving this kind of range equation, which normally we'll write this as R, or you'll see it in both ways. So let's just get a little bit of practice working with it, right? So the strategy for answering this problem is that this is clearly an example of projectile motion. If we just kind of assume that when he springs off, we'll take all of that as being instantaneous, right? In reality, there's a finite amount of time of extension. We're going to ignore that. It just suddenly jumps to a certain speed at 45 degrees, and we want to know, assuming it's on a big, long, level field, we want to know how fast it had to jump in order to get this 1.8 meters that it's known to be able to do. Okay? So we're given a launch angle, as well as the projectile range, right? 1.8 meters is delta x. We have the launch angle. We can assume that gravity is a standard 9.8. So we really have all the necessary information to use the range equation, right? You see there's only one thing missing, and that's the exact thing that we want to solve for, which is the initial velocity. Right? So this is a one-step problem, right? So the only reason I am working this one-step problem is because there is some interesting, there's an interesting tidbit here. We'll get to that in the end. It turns out that there's actually two answers, okay? So let's rearrange the equation that we have, which was this, to solve for the thing that we want, right? We'll try and get initial velocity by itself. So again, at first, as we go further and further on in the sequence, we're going to start skipping steps a little bit because you're all probably okay with math, but let's not do that at first. I'm going to multiply both sides by g, which then gives me vi squared sine 2 theta. And then I'm going to take this and divide the sine 2 theta on both sides, right? So this is now over sine 2 theta, and that leaves vi squared by itself. Take the square root of it. And we're going to plug in numbers now. Right? So if we plug in numbers like this, we get sine of 2 theta. Theta was 45 degrees. We get this answer. Okay. So actually, in this case, we get one answer. But I'm about to ask you something. Oh, I think I just blew it. Okay, never mind. Anybody have any questions about this? Yeah. Why is it not minus 9.8? Good question. Let's go back and figure this out. I've had 3 hours sleep. You guys are gonna have to help me out today. Okay? Got back late from. It was a good show, by the way. Hamilton. It's a good show. Vi squared delta x g. Oh. Why is it not minus g? Because the original equation, this is the range equation, I didn't plug in for a. If this had been an equation that said a, then you would have to be careful about what direction g goes. But go back to the last lecture, and we derived this, and when we derived it, we plugged in a minus g, and it canceled another minus sign, and we ended up with a positive. Okay? Yeah?
So whenever g is in this equation, it should always be constant?
Yeah. I mean, different books have different notations, but most books stick with the idea that little g is positive 9.8. Okay? And then it's the acceleration that's going to change sign depending on which way you decide points up or points down. Okay? But typically, and in this class, g will always be, little g will be positive 9.8. Okay. So we were here. We got 4.2 meters per second as the initial velocity. Okay? So now let's try and do another question. We just saw that the kangaroo rat can jump at a horizontal distance, blah, blah, blah. At what angle would it have to launch to land at 0.9 meters away? Okay, and you guys can work together on this. Let's think about how you could figure this out without doing a whole lot of math, right? And the key is the scaling. Notice that, so rather than recalculate from scratch completely, let's make use of the fact that we had already just done a problem where we said that it could go 1.8 meters by launching at 45 degrees, right? And we're assuming that the initial velocity stays the same, right? No, I'm sorry. The angle stays the same, and now we want to know what the new velocity is, right? So the angle stayed the same. Did I get that right? What angle would it launch using the same? I'm sorry, I'm again, not enough sleep. So we were asking what angle would it have to launch at if we assume that the leg muscles always go full power, right? So it's always launching with a total velocity of 4.2 meters per second. The last time it did it at 45 degrees and got 1.8 meters. This time, it does it at a different angle and gets half as far, right? So we just spent like 10 minutes last week looking at the range equation and asking, what does this mean when this is halved, this is doubled, right? And we can see that if I look at this, the range, right, goes as sine of 2 theta, right? And if the velocity, if g is the same and vi is the same, this is just some constant out front. So really, if I want this to be cut in half, I just need that to be cut in half, right? To determine how to change the angle to achieve half the horizontal displacement, we're going to look at the original form here. We're trying to cut the displacement in half while keeping vi and g the same. So in our original calculation, the launch angle was 45. So that sine of 2 times 45 is equal to 1. So we just need this value to be cut in half. It's a little, because of the 2 theta, it's not so easy to grasp. So think about that for a moment. Right? We're just saying that this whole thing, right, this is constant, and I want to cut this in half, so this whole thing has to drop to half. Right? So sine of 2 theta nu, instead of being 1, which is what it was when it was 45 degrees, now has to be 0.5. Right? So our goal is just to find the angle where sine of this new theta is equal to 0.5. And we can take the arctangent of 0.5 and take the arcsine of 0.5, and we find that is going to equal to 30 degrees. Right? So inverse sine of 50, or 0.5, is 30 degrees. But that means that 2 theta is equal to 15 degrees. Right? So theta nu is half of that. I'm sorry. Really need more sleep. Inverse sine of 0.5 is 30 degrees, but 30 degrees represents 2 theta nu. So theta nu is half of this angle, which is 15 degrees. Okay? Who was able, I don't want people to raise their hand and feel like they're lost, but who was able to follow that logic? Okay, large majority of you. So if you're not, send an email, and I will clarify through maybe a more clear webcast or something if people need it. Okay. Oh, but wait. Remember that trigonometric functions are defined on a circle, right? So there are 2 places where sine of theta, there are 2 angles where sine of theta is positive 0.5, right? This angle right here, sine of theta is just the rise, and that's 0.5. The run is, I think, 0.866 or something, positive 0.866. But if I take this other angle over here, right? If I look at this angle, 180 minus 30 degrees, that also has a rise of 0.5 and a run of negative 0.866, right? So not only is 30 degrees an answer for this, but so is 180 minus 30, which is 150. Was the answer for the intermediate stage of 2 theta is equal to this, right? That stage of taking the arcsine, right? So the arcsine of 150 and the arcsine of 30 give me 0.5, and we were supposed to take half of that, so it turns out that it can either be 15 or 75 degrees. And this makes perfect sense if we start to think about, what did we say? When we go to 45, remember we did this whole, what does sine of theta tell us? It was sine of 2 theta, so when theta got to 45 degrees, sine went to sine of 90 degrees, which is 1, which is maximum. which means 45 degrees is the angle where you're going to get the maximum range. And by definition of maximum, that means 46 and 44 degrees both are less than maximum, right? So you can have this. Here's where it lands. It's at 45 degrees. But as you go either higher or lower, it falls short. One at a low trajectory, one at a high trajectory, right? And so 15 degrees and 75 degrees both land at the same spot. One's just a really big high jump, and the other's kind of a little skip jump. Any questions? Yes? When you are asked for an angle at which you'll get a certain displacement, with a few exceptions, namely this one, right, you can get two answers, right, unless there's other constraints in the problem that make it so that one of those answers is invalid. For instance, if you're trying to kick over a wall, right, in which case one of them would just hit the wall and not make it over. One's a line drive, one's a punt.